Hey everybody, it is good to be back. It's been a while since I was able to stream some balloon science to everybody. I have had some technical difficulties with my laptop on the road here and have gotten it all in order. I got a temporary replacement one. So today we're going to take a look at a French balloon paper from the BALSAMINE project back in 1979. So let's see, is there any administrivia to get to? No, I don't think so, other than thank you to my patrons on Patreon. Tons of people now, 11 people. We'll go through all their names at the end. Please consider supporting to keep this stuff going for equipment and bandwidth costs. It gets expensive sometimes. So I can bring you more stuff, including live from the field and more papers and stuff like this. So let's go take a look at BALSAMINE. So let's find our PDF app. The BALSAMINE Experiment by Daniel Cadet and I believe Henri Overlay from Laboratoire de Météorologie Dynamique in France. So right away we see the BALSAMINE Experiment is an acronym for Balloon Superpressure pour l'analyse de la mousson indienne d'été. I think I pronounced that close. So it looks like superpressure balloons for the analysis of something in the Indian Ocean. Maybe the motion of the atmosphere over the Indian Ocean. And this was performed from May 15th to July 15th, 1979, during the Arabian Sea phase of Monex, to study the monsoon circulation over the Arabian Sea phase of Monex, to study the monsoon circulation over the Arabian Sea using superpressure, constant level balloons. Superpressure balloons are by definition constant level, and that is because the buoyancy equation for a balloon is density. It's been a while since I explained this. But anyway, the density of wherever the altitude where the density of the balloon equals the density of the air, when those two are equal, the balloon will hang like a buoy. At the ground, for example, balloons typically have a density less than air, which means the air wants to scoot underneath the balloon and the balloon wants to get over the top of the air, as if you had a float underneath the water. The water wants to get under the float and the float wants to get over the water because they are basically, water's heavier than the float at that depth or altitude. So what happens when you have a float that is equal to the density of the water? Well, that's exactly what we have in submarines or fishes, where they control their depth by modulating their weight, basically by adding water or removing water or expanding an air chamber or retracting an air chamber. And the density formula is mass over volume. So in order to change your density, you could change the density of the gas or the water outside, which is possible by changing altitude, or you could change the density of your vehicle inside that gas or water. And to change density, you can change either the mass or the volume. Now, changing mass is easy. You can drop things away from the vehicle. Harder to add mass, but it is possible. So if your goal is to stay at one particular altitude, you want to make sure your volume does not change and your mass does not change. Now, mass is easy for a balloon to conserve. Just don't drop anything and don't gather anything in from the outside. However, to keep your volume the same is very difficult for a balloon. Balloons, as they climb, because the air pressure decreases, the helium wants to expand to fill basically the gap that was left by the air pressure reducing outside. So as the helium expands to meet the decreasing air pressure, the balloon's volume wants to increase. The force of the gas inside pushes outward until it's equal to the pressure force on the outside from the air. And if your balloon volume changes, that means its density changes, and volume being on the bottom side of the density equation, that means if the volume increases, your density decreases, which means you're still lighter than the air around you. Even though its density has decreased, yours has too. So you're still going to be lighter, and air still want to go underneath you, and you're still going to want to go on top of the air, rising. And as you rise to lower density air again, your balloon expands. So this cycle just continues essentially indefinitely. As you climb, you expand, and therefore you keep wanting to rise more. So that's what keeps balloons rising continuously all the time. So if you want to stop and just float with a balloon, you got to stop that inexorable process of expansion. And that is what a superpressure balloon does by rigidly holding the volume fixed. It's not rubber, it's usually plastic, and that basically as the helium expands, at some point it fills up this plastic bubble and rigidizes it, and then starts pressurizing. As the balloon continues to climb, the pressure inside can't expand, and at some point your mass and your volume in that density equation causes your density to equal the density of the outside air, and you stop climbing. So that was a little bit of a muddled explanation of superpressure, but we'll get into the mathematics more detail in a future video. So 88 balloons were equipped with temperature, humidity, pressure, and overpressure sensors. Pressure sensors are here referred to as barometric pressure. That's outside ambient weather pressure used by altimeters to measure the altitude of the balloon vehicle. Overpressure is a sensor that is used to measure how much pressure is inside the balloon relative to outside. Remember I said that the balloon will pressurize because it keeps rising, and the air pressure keeps decreasing on the outside until it stops and levels off. And this monitors for engineering purposes, troubleshooting purposes, how high the pressure got on the two sides of that plastic envelope that's rigid. So they were released from the Seychelles Islands in Diego Suarez. I don't exactly know where those are, but we will see in a later map. Let's see if we can just find it. There's a map towards the end of where this all happened. So we see they were launched from Seychelles and Diego Suarez in Madagascar. So we see India up here. Do I have a nice highlighter? Tool, note type, freehand. So we see, oh, I don't like red. Let's find a yellow highlighter. Show lines. I know you can't see, but note type, freehand. Show colors. Banana, sure. That didn't work. Freehand. Show colors. It's banana. Where did red red come from? Show lines. Maybe I can't. I'll have to dig into this more later. Highlight. Not quite what I was looking for. Note type, freehand. Well, looks like we have red lines to play with today. So we see India here, and Saudi Arabia, the Arabian Peninsula there, Africa here. Okay, let's go back up to the top. The platforms were located, and let's go back to highlighting. I apologize. I've not used this app much. This is a new app. Text tool. There we go. Platforms were located, and the meteorological data was collected by the Argos system aboard the Tyros N and NOAA 6 satellites. So Argos was NOAA's, I think it was their very first satellite data collection system for weather experiments. And Argos was used for everything you can imagine, from like whale tracking to ocean buoys to balloons, lighthouses, weather stations far flung out around the Arctic and things like that. It was very crude. It didn't allow much data to be transmitted, but it worked. And as you can see, there were only 2 satellites collecting it. So Argos couldn't get a data stream. What experiments had to do was store up reports of data throughout the day and wait to hear a satellite announce that it was overhead and ready to receive a dump of stored listings of collected observation data from that. Turn the heat up here. From that particular experiment. During the experiment, which would be BALSAMINE, the positions and data were received in our laboratory on near real time, delay of about 1.5 hours. So the satellite would go overhead, apparently. One of the 2 satellites would pass over the balloons every 1.5 hours. After about 15 days after the end of the experiment, the first results can be given. So this paper was published in, let's see, July. That was May to July. When was this paper published? Yeah, look at this. This paper was published 15th of July. The experiment ended on July 10th, so that is pretty darn quick. Where did my PDF go? I think my PDF reader died, even though you can still see it. Yep, it did. Well, that's not promising. Open, 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 open. Stand by, folks. I will be right back as I figure this slight glitch out. Hey everybody, we're back. We have resumed PDFing. Okay. So the BALSAMINE platform consists of a non-extensible Mylar 2.5 diameter envelope. What is 2.5 meters in feet? About 10 feet, I think.
8.2 feet.
8.2 feet. Okay, so Mylar was, clear Mylar was a material of choice for a lot of these long duration balloon projects by the US in the 60s and 50s, and by the French to very recently, almost today, they have been using the Mylar spheres. Sensors and associated electronics, the necessary electronics, power supply, and antenna to transmit 400 megahertz signals to the TIROS N and NOAA 6 spacecraft once every 40 seconds. So, we take our little asterisk here and see that the envelope was designed by Zodiac Espace for CNES, or CNES, the French space agency. Zodiac, by the way, is the same company that builds rubber boats, inflatable boats. They branched out into building inflatable balloons back in the 60s, I believe. That same company, the balloon division, is still building balloons for France today, though they have changed hands and changed names several times. I want to point out that 400 megahertz signals are the same frequency that all of the weather, a lot of the worldwide weather equipment still uses today. From 401 to 405, I think, is an internationally recognized weather data transmission band for satellites and for ground stations, like weather balloons. So I got a little ahead of myself, and I think that they did not actually transmit bulk packets of data. I think they actually transmitted just single report packets every 40 seconds to the satellites. So I guess they would not get data from the times they weren't transmitting, or the times the satellites weren't overhead. The electronic equipment, except for the ambient sensors and the antenna, is placed inside the envelope, inside the balloon itself. That means there's not a box of electronics hanging below, which is quite unusual in ballooning in general. Let's go find figure 1 to see what that looked like. How exotic. We see the lovely spherical Mylar and the box of, here's my little note tool, freehand. Yeah. We see here is the payload, all of the business parts of keeping a balloon alive, batteries, transmitter and data encoder and pressure sensor, outside pressure sensor, an antenna for transmitting, and I believe solar cells here. We have wires running down to an air temperature sensor, and wires running down to a humidity sensor there as well. Very neat. A white plastic container attached to the lower pole of the balloon housed the power supply. As we saw, the transmitter, oscillator, data encoder, and pressure transducer. The antenna, second transducer, yeah, we looked at all this. The inside design was specially developed for balloon flights in the tropical boundary layer in 1975 and 1976. And that is a really interesting design, to have all of this stuff inside the balloon instead of hanging below it. And it wasn't, there was a very specific reason for that. And that was because in the tropical areas where they wanted to sense weather, they wanted to do it at lower altitudes, not in the stratosphere. And that means that these balloons are going to encounter weather, and in particular rain. And when you have water that falls on the surface of a balloon, like on the top side of the balloon, here, it sticks. There's some amount that sticks, that beads up, as you've seen on windows and surfaces. Even though some of it runs off the sides, the amount that sticks, and also from just the simple force of the rain hitting it, causes the balloon to add mass and have a force that pushes it down. And so, as we know from the density equation, adding mass is going to make you denser, which is going to make the balloon seek a denser air layer below. So when you get rained on as a balloon, you sink. And in the tropics, at the altitudes these balloons were flying at, that meant they could sink all the way to the ocean and hit the water. But this design that sealed all the electronics inside allowed them to hit the water, and when the rain stopped, take off again back into the sky. So these balloons will go down, flop onto the ocean, get washed around during the rain, and then dry off and take back off into the sky and resume their mission. Is that not crazy? So the platforms were located on we already read that. Message duration is less than 1 second. Wow, that was fast transmission. Including unmodulated continuous wave and 256 bits of data. Well, it's fairly easy to transmit that short amount of data. They obviously packed a lot of information into a very small packet. 256 bits would be that divided by 8. Is that 8 bytes? What is 256 divided by 8?
The answer is 32.
32 bytes. Simple math. So 32 bytes was all they had for satellite ID, humidity, temperature, 2 different pressure measurements, probably like battery voltage. They might tell us later on what their telemetry content was. During a satellite pass, about 12 to 15 messages can be received aboard a satellite. For the BALSAMINE experiment, this high probability of message reception was used, and messages were subcommuned to transmit 4 by 256 bits of data in 4 successive emissions. So I think, what the hell does subcommuned mean? Subcommuned. What is this? What does subcommuned mean?
Here's what I found.
Subcommuned. I think that means in a close cluster. Subcommuned. Feel free to say hi in the chat or the Facebook comments. Subcommune. Definition. Subcommune. Definition. Okay, there's a clue here, a French translator. that doesn't help. Anyway, subcommune, we'll just assume that they were grouped together, close together in time, and just repeated the same bit of data. That's my guess. The location of each platform is determined solely by measuring the Doppler effect on the carrier frequency of incoming messages. The accuracy of platform location depends on the accuracy with which the platform altitude is known, i.e. the altitude of the balloon, the stability of the oscillator, that would be the main component of the transmitter, generating its transmit frequency for the data carrier, and the availability of information concerning platform speed and variations therein. Wait, do they mean platform as satellite or balloon? Maybe I've been reading this. No? Oh God, I think platform is the balloon. The location accuracy is better than 5 kilometers, and the accuracy of speed determination is better than 1.5 meters per second. Location accuracy of 5 kilometers seems like trash today, now that we have GPS and GLONASS and Galileo and various global navigation satellite systems, but was amazing precision back in the 70s when one satellite was doing the location, and it was doing it just by hearing the tone change of the radio frequency as the satellite passed the balloon transmitter. I'm curious how they determined the axis of the balloon relative to the satellite as it passed, if it's just based on ranging, because Doppler will only give you the distance from your transmitter to your receiver and the speed at which you are traveling past it. I suppose if you knew where the satellite was going precisely, let me draw this here. Let's go down to a map. Let's hypothesize a way that the satellites might have known where things were going. So, if we on, so is there like a little palette I can keep these tools out with? No. Control Apple 8 and 9. Right, so if we have a line where the satellite is going, and we have we'll say a balloon here, you ought to be able, you can you know the distance. Oops. So say, can we adjust this? Yeah. So if your satellite's here, we know the distance from here to here. And then as we get farther up, we know the distance from here to here. And then as we get even farther up, we know the distance from here to here. However, it doesn't tell you, like, that's not true. You don't know the distance. You only know the time that it takes for the frequency to change. And you know the midpoint of when the frequency starts getting lower, like as you're hurtling roughly towards the satellite, towards the balloon this way, the tone is getting higher and higher and higher and higher in frequency, like a train passing. And then as you start going farther past it, it's getting lower and lower and lower and lower. So you can time how long it takes to sweep up and down, and because you know the satellite speed in position, the time that it takes for this to sweep up and then down should be able to give you the destination, how far away that this triangle has to have an apex of. However, that doesn't tell you whether it's left or right of, left or right of the satellite. It could be over here. A mirror of the solution is on the other side of the satellite path. And I think that's why they said that it was important to already know something about the position of the balloon. And that's to resolve this mystery of what side of the satellite's path that your balloon is actually going to be on. So that sort of makes sense. That's pretty cool. I suppose you could do that with a train too. So this is a long paper. We'll probably split this into a couple of sessions. I tend to talk a lot and it takes a long time to get through these papers. I don't actually pre-read these, I just skim through them to give you guys, just to see that it's going to be interesting. Let's turn down our music a smidgen. There we go. Let's see, where were we? Okay. The balloons were equipped with, is our music going crazy? I haven't heard this song before. It's just picked up some speed, that's all. I think this song is not my favorite. I think I might skip songs. Can I do that? Oh, well, it skipped itself. So the balloons were equipped with five sensors to measure the pressure, the overpressure of the balloon, the air temperature, with two different sensors for air temperature, and humidity. The pressure sensor was specifically developed by our laboratory, LMD, for balloon flights in the boundary layer. The boundary layer is the atmosphere that's closest to the ground, and that explains why these balloons were at high risk of splashing into the ocean during rainstorms. It uses a capacitive coupling with an aneroid capsule. Oh, that is so old school. So old school. So an aneroid capsule is basically just a sealed accordion, a little metal accordion box, welded shut with a certain amount of air in it, like at sea level. And as the air pressure outside decreases, the air inside wants to press outward until the pressure inside is equal to the outside. So as the pressure outside decreases, all of a sudden there's more force. And as it expands, the force decreases. And so literally this little accordion swells or contracts as the altitude changes. So as you get high altitude, it gets big. And as you go down to sea level, it's flat. And when they say it uses capacitive coupling, they basically just had an electronic plate on the capsule and another electronic plate. And as they got closer together, the distance you can measure through an RC circuit. You can electrically just measure the distance between two plates in a very simple way. Hard to calibrate, particularly over a long range, but it's what they had. Here we go. Oh, wow. Pretty good. Not, I mean, terrible by today's standards, but 0.3 millibars, including temperature drift. Temperature drift. So a metal can is gonna the skin is gonna expand and contract with temperature changes. The humidity sensor is a thin film humidity sensor based on the humidity sensor developed by Vaisala. Oh, they've got umlauts and things on the name Vaisala. the company still exists to make precision sensors like this in Finland, but it does not have all the little extra character accents, grave marks, or whatever they're called. The sensing element of the humidity sensor was used and associated to an electronic circuit developed by LMD, again, the French Meteorological Laboratory. I had the pleasure to visit them about, going on 8 years ago now. Visited Albert, I've forgotten your last name for the moment. Herzog, Albert Herzog, I believe. The accuracy of this sensor, calibrated before launching, is about 3%. The first temperature sensor is similar to the one used during the Éole experiment, which is the massive thousands of balloons project by the French. The sensing element itself is a Vico microbead thermistor. Those are still sold today. We got some for testing on Project Loon when I worked there, with lead welded to gold strips, vacuum deposited on a thin optical glass support. Yeah, that's straight up out of the Éole program. I remember analyzing that structure. We'll look at Éole someday. The temperature accuracy is better than 0.5 degrees C, but it is very fragile, being very thin glass and like a hair-fine resistor wire. The second temperature sensor is identical to that used for radio soundings, about 1 degree C accuracy. This can give good measurements if the Éole sensor breaks. Now, the ones used for radio soundings are bound to be bigger and thicker and susceptible to solar radiation bias in the daytime. They get hot in the sun. All the sensors have been calibrated at LMD except for the humidity sensor, calibrated before launching. And that's still done today. Radio sondes usually calibrate their humidity sensors very recently before launching. All the measurements are taken within a few minutes every hour, then recorded aboard the balloon. Oh, I was right back then. It does bulk package up the data. During 4 successive emissions, was it transmissions? This was translated from French, by the way, back in the 70s. The balloon emits the last 16 hours of measurements. Yeah. So the satellite should be able to pick up all of the data recorded while the satellite was away. The words corresponding to humidity and temperature measurement are 9 bits long, whereas the pressure word is 12 bits long and the overpressure word is 11 bits long. So, how long is that? So, how many numbers can you store in that? So we have, what is 8 to the 9th power? I think that's how you do it in binary.
8 raised to the 9th power is 134,217,728.
Is that right? What is 8? What is 8 to the 4th power?
8 raised to the 4th power is 4,096.
That's, yeah, okay, that's a lot of numbers. Anyway, my brain is not quite working on the decimal to binary conversion. Isn't quite making sense. At some point, there's going to be they're going to have a decimal point in there. They're going to make this an integer and just multiply the actual value by like 100 or 1,000 to give you basically a long string of numbers. Like if it's 23C, they're going to send like 2300 so that you get 2 zeros of decimal precision. Timing of the experiment. When planning the experiment, it was decided to launch balloons at a rate of 2 balloons per day. Oh wait, let me step back a second, because it's very likely these balloons were not sending temperature, they were not sending humidity. There were no computers on board whatsoever here. This was straight analog, like voltage readings from temperature sensors and humidity sensors. And what this was probably doing was simply digitizing the range of voltage that the sensor could output and just transmitting the voltage itself. And back then that would have been the only really reasonable way to do this. And computers were big and large, and it would have been unnecessary to actually convert to a number like 23C before transmitting. You just transmit the raw analog input value of like 8.79234 volts, which on the ground you have a lookup table that says what is 8.9237 volts equal 23.0 C temperature. When planning, it was decided to launch balloons at a rate of 2 per day from 20 May to 10 June from the 2 launching sites, and after June, 1 balloon per day from Seychelles. However, during the experiment, due to the delay in the burst of the monsoon, provoking balloons' destructions within the ITCZ from Seychelles Islands, that's the Intertropical Convergence Zone, I think. What does ITCZ stand for?
I found this on the web.
Yeah, close, but no. Or balloons crashed in Africa from Diego Suarez. The launch planning table was modified. This was possible because data reached us, in the field, mind you, by telex and telephone within a few hours after satellites had received a balloon, mainly Tyros N, because NOAA 6 was launched on June 27th and became operational a few days afterwards. Damn, that's cutting it close. Your satellite to receive data wasn't launched until your project was almost over. The latest location, as well as a message, were received and processed on a computer using calibration curves. This information was sent back to the launching sites, which were received within a few hours. Launching sites informed us of latest launching sites. What? Through a manual Argos data collection and location platform. Identification number of the balloons, as well as identification number of sensors and humidity calibration points were sent. With the near real-time system, I think that means they had a receiver to downlink satellite data at the launch site, maybe? Identification number of the balloons, as well as identification number of sensors and humidity calculation points were sent. No, sorry, it was a transmitter. This was to send all the calibration data per balloon to Mission Control in France. With near real-time system, we were informed, as well as the launching sites, of the evolution of the experiment, and it was then to modify flight level, launching rate, calibration, etc. After a few days, due to reduced lifetime of the balloons, it was decided to modify the launching rates up to the burst of the monsoon. And when they say burst of the monsoon, they don't mean balloon, they mean when the monsoon, I think, just starts dumping rain. Then, after 25th of May, 1 balloon per day was launched from Seychelles Islands and 1 every 2 days from Diego Suarez. After the burst of the monsoon, around 20 June, 2 balloons per day were launched from Seychelles and 1 from Diego Suarez. A total of 88 balloons were launched. 2 balloons were not launched from Diego Suarez because helium was lacking. It sounds like it was not showing up for work, but they ran out of helium. So these were not particularly long duration balloons, but the mean lifetime of the balloons is about 4 to 5 days. But it does increase after the burst of the monsoon, and some balloons lasted 6 to 7 days. The lifetime is reduced compared to that obtained in the 1975 experiment, because during the first phase of the monsoon, just after the onset over the Arabian Sea, the speed of the flow is large. During this phase, the trade winds crossing the equator between 45 degrees east and 60 degrees east strike India. This was also noticed at the beginning of the 1975 experiment. Thus, lifetime is reduced by orographic barriers of the west coast of India. What does orographic mean? What does orographic mean?
Orographic means relating to mountains, especially with regard to their position and form.
I.e., balloons hit mountains and crashed. Or the air parcel they were in hits the mountain and has shoved over it, and when you shove a superpressure balloon up too high, the pressure inside stays the same, but the pressure outside keeps decreasing and decreasing, which means essentially it's as if you're pressurizing the balloon more and more and more until it pops. So just having the balloon be forced up over the mountains, even if it didn't hit the mountains, is going to cause it to burst. Okay, so the data received on near real time are too fragmentary to show curves of flight level or temperature and humidity variations. That's interesting. All the data, oh, I see. This wasn't the full packet storage of 16 hours. This was just little snippets that they were receiving in the field, I think. All the data are on magnetic tapes and will be processed within a few months. Damn, back in the old days of computing. The designed flight level was 900 millibars. However, balloons experienced height variations due to the diurnal cycle and rain showers. The difference between the two temperature measurements is weak, about 0.5 C during the day and 0.2 C during the night. This was due to the difference of sizes of the sensing elements. The EOL microbead is tiny and gives more realistic measurements than the meteorological radiosonde sensors. The humidity sensor worked quite well. During the weeks prior to the burst of the monsoon, humidity was important, 85% near the equator. During the onset, when ITCZ moved northward, a decrease of humidity was noticed near the equator. From a quick look at the data, it also seems that humidity within the tropical boundary layer increases while the balloon flew towards India. Weather data, we'll skip over this. The BALSAMINE experiment gave low-level quasi-Lagrangian trajectories during different phases of the monsoon, before, during, and after the onset. Some early results have already been deduced. Processing of the data is being made, and we hope to end this work within a few months. Acknowledgements, lots of acronyms. Figures and captions. And references. Looks like good papers. I'll have to go dig for those sometime. Here's our balloon, just a little review. Your spherical mylar envelope, which was 2.5 meters across. 2.5 meters. And that was made of a clear, strong plastic mylar. And your electronics were all stuffed here inside of the helium chamber, sealed away from water and rain, with the solar panel up here and your antenna. Your temperature sensor and your humidity sensor, called a hygrostor. here are some of the flights. And these, the numbers here represent, I believe, the day of the year. And, sorry, I believe the number on the left is day of year. And this is mission elapsed time. Shall we draw on the trackpad? Could be worse. So we saw this balloon wandered here. These dots are just from their real-time observation of occasional satellite passes. As they said, all of the data recorded got dumped to tapes. They didn't see all of it as it was happening. Oh, no, I think this is wrong. These don't make sense as mission elapsed time. I think that's time of day. Say hour. Day of the year and hour of the day. So that's midnight, 6 a.m., 12 p.m., and 6 a.m. again. Midnight, 1 p.m. And this would be, I believe, the launch dates and the launch hour. These, of course, I believe would have been a reference to Universal Coordinated Time. So these were launched on the 145th day, and we see this one got to here by the 150th day. These lasted from day 147 to day 153, day 150. So 3 to 5 days is about what they're surviving for. I really didn't go far. Oh, they said towards the end of the monsoon season, they weren't being destroyed by the monsoon anymore, and they were making it to India. As we see here, orographic mountain features. We're terminating them. Oh, much longer here. Well, no. Still only 5 days, 186 versus 181, but maybe 6-7 days, but much faster winds. And there we go. There we have it, everybody. That was the French BALSAMINE superpressure balloon program. Nice little technical paper about the structure of the balloons and the operation of the project. So thank you for joining me today. I appreciate it. It's good to be back talking balloon science, and I'd love to have conversations with you guys. Feel free to contact me to join in on like an audio chat as we stream about balloons with your questions and comments. So with that, I would like to thank my patrons, my Patreons, my patrons, Mike Bowen, Sheila Bunch, Lee Grainer, Ben Lathan, Ken Howard, Sophie Searcy, M. Fong, Steve Randall, Ashley Meyer, Robert Quattlebaum, and Martin R. Rothfield. Please consider donating at patreon.com/BalloonSciDan, patreon.com/BalloonScience.